Hello everybody. After we have seen so many of applications of the Dedekind product theorem, it is actually time to finally prove it. So let's remind ourselves the statement. So we have essentially three fields here. We have a field F, and then an finite extension K, and a finite extension L. This extension here is of degree n, and this extension is of degree m. And then we take vectors L1 through Lm, which are elements in L that are a basis of L as a vector space over K. And we take elements K1 through Kn that lie in K and are a basis of vector space. They're a basis of K as a vector space over F. And then the statement of the theorem tells us that if I take all the possible products of the elements from the set of the L's and the set of the K's, then I get a basis of L as a vector space over F, over the field at the bottom. Okay, so let's prove this theorem now. The proof is actually not that complicated. It's just really a reminder of what it means to be linearly independent and what it means to span. So let's let L be an element of L. Then, because the Li's are a basis of L as a vector space over K, I can write L as alpha 1 L1 plus alpha 2 L2 plus ... plus alpha m Lm for some alpha 1 through alpha m in K. Right? I know that these are a basis of L as a vector space over K, so I can write every element of L as a K-linear combination of these elements here. Then these guys lie in K, the alphas, so I can now use the fact that I can write them as an F linear combination of the various Ki's, because these little Ki's are a basis of K as a vector space over F. So then each alpha I can be written as alpha I is equal to beta I1 K1 plus beta I2 K2 plus ... beta In Kn for some beta Ij's in F. Okay, so putting it all together, I'm going to use the sigma notation now because there are too many elements to write. So I can write then L as the summation so first of all, alpha 1 is a sum like this and alpha 2 is a sum like this. So I get a summation of over I and over j. So let's say the i's were numbering the l's, so it'll be summation from I equal 1 to m, summation j equal 1 to n, beta I j k j times li. Right? Note that all I have now done was this here, this bit, that is just alpha j. Sorry, that's just alpha I. Right? Alpha I is that summation here. So I just replaced alpha I in this sum. I replaced each alpha I in this sum by this expression. And then I used the sigma notation. Okay, so when you look at this, I now get a combination of these products, just like we claimed. And these numbers here, the beta ij's, and these numbers are in F. So I was able to write my L as an F-linear combination of the products. So that means the products actually span L over F. So this set Likj, as I goes from 1 to m and j goes from 1 to n, spans L as a vector space over F. All right, so what remains to be proven is that these products are linearly independent. So let's now show that the Likj's are linearly independent. Over F. Well, how do you show linear independence? You write a sum with some coefficients in F, set it equal to 0, and then you want to show that all the coefficients must be 0. So suppose certain summation over I and j, so I equal 1 to m, summation j equal 1 to n. So I'm not going to use these beta ij's because they were for this particular L, but say some summation, let's say aij k, so I guess I use kj li is 0 for some aij in F. Okay, if I write this out, this sum, I get the following. So I do, first I take I equal to 1, so I get A1, 1, K1 plus dot 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 plus A1, J goes up to N, so N, K, N, L1 plus A2, 1, K1 plus dot 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 plus A2N, Kn plus, and finally the last term is going to be AM1, K1 plus AMN, Kn, and this is 0, right? So I get that this is 0. But note, the aij's are in F. So in particular, they are in K. Because F is a subfield of K. And all the K's are in K, so that means this is in K. And this is also in K. I forgot the L's here. So this is L2 plus Ln. And this is also in K. Right? Not the L's, just the things in parentheses are in K. All right. But since the Li's, so since the set L1 through Lm is a basis of L over K, it is linearly independent over K. And look what I have here. I have a k-linear combination of the Li's giving me 0. K-linear combination of Li's giving me 0. And because the Li's are linearly independent over k, that means each of these coefficients must be 0. So a11k1 plus dot 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 a1n kn must be 0, and a21k1 plus dot 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 a2n kn must be 0, and so on. All of them have to be 0 at the same time. Okay, but now if you look at these, each of these equations, you see the AI's, the AIJ's are in F, which means this is now an F-linear combination of the K's that gives me 0. This also is an F-linear combination of the K's, and this also is an F-linear combination of the K's. Each of them gives me 0. But the K's are a basis. Now, as the K1 through Kn is a basis of K over as a vector space over F, the Ki's are linearly independent. Over F. So, because the Ki's are linearly independent over F, and this F linear combination of the Ki's gives me 0, that means A1 all the way through A1n must be 0. Now looking at the second one, again the Ki's are linearly independent over F, and the A21 and so on lie in F. So all of these AI's have to be 0. So proceeding like this, I get that all of them have to be 0. So Aij is 0 for all I and j. Oh, but that going back to this sum, that means all these coefficients must be 0. Let's call this star. Hence, looking at star, we see that we have proved that the set K, J, L, I, where J goes from 1 to N and I goes from 1 to M, is linearly independent. Over F. Right, because we set it equal to 0, and we have now shown that all the coefficients in this equation must be 0. So this proves linear independence. So that means the set of products is linearly independent over F, right? The AIJs were in F. So we have shown that the products Kj times Li span L as a vector space over F, and now we've shown that they are linearly independent, so they are a basis. So this finishes the proof of the Dedekind product theorem.